Page 47, isosceles and equilateral triangles. We already did something with isosceles and equilateral triangles a month ago, maybe a month ago. So this should start coming back to you. We've just not been practicing with them every single day. Isosceles triangles. That is a triangle that has at least two congruent sides. The congruent sides are called legs. And where the isosceles triangles, do you remember what I said to turn it like? Turn it like a rooftop. Because then it would help you to know which sides are congruent, and then it would help you to identify what's called the base. The base would be what it's sitting on at the bottom. The two sides that are congruent are called the legs of the isosceles triangle, which makes sense because ideally your legs should be the same length, although everybody's different. Some people have slightly. My son has his right foot is bigger than his left foot. Then at the top, when you turn it like a rooftop, so the angle at the very top has a specific name. It's called the vertex angle. We'll put the abbreviation for angle because we don't have room. The angles at the bottom, since they are on the bottom and they are on opposite sides of the base, they are called a base angle. I wish you could see too that the board is shaking, or not the board, but the projector is shaking. So when we have an isosceles triangle, we have two sides congruent. I'm going to emphasize these congruent marks. Turn it like a rooftop. Let's make a note. Like a rooftop. Then you can find the congruent legs, the congruent base angles, the base of the triangle. Now, when you know you have an isosceles triangle in front of you, some stuff happens, and it's because it's an isosceles triangle. So down here in this next section is 3 theorems to let you know if this is what's marked, then you can say this. If this is what's marked, then you can say this. So it's all about what's marked, right? So if we look at this picture right here, this picture has what marked? The legs are marked as congruent. So if side AC is congruent to side BC, which means the legs, right? If the legs are congruent, we're going to put that in parentheses, because that's basically what it's saying. If the legs are congruent, then you can say the base angles are congruent. Base angles congruent. So if you have a triangle with 2 congruent legs, then you can turn it like a rooftop and you can mark the base angles congruent. Now look at the next one. What do you notice happened? What do we have here? We have 2 angles congruent. Remember we said however many congruent sides dictates the number of congruent angles, and then the same is true for the angles. However many congruent angles is telling you secretly how many congruent sides there are. So if the base angles are congruent, then you can mark the legs congruent. Notice that the 2 things we just filled in are the complete reverse of each other. Do you see that? That is called an if-then statement. It's conditional, meaning if you meet this condition, then this is the result. If you come in the door after the bell rings, then you are tardy. That's a conditional statement. If you come in the door after the bell rings, then you're tardy. Now I'm going to switch it. if you're tardy, then you came in after the bell rang. Is it still true? Yes. So this is an if-then statement, and they have switched the condition and the consequence, and it's still a true statement. So, which brings us to the third one. The third one's a little new. If a line is bisecting the vertex angle, this is important. It has to be the vertex angle of an isosceles triangle, not just any triangle. It has to be isosceles. If a line is bisecting the vertex angle, this is the vertex angle up here, then that line is dropping perpendicular to the base. Okay? So basically they're saying if we have an isosceles triangle, so we have AC congruent to BC, and we know that line CD has just cut that vertex angle in half. So trace these angles carefully. We have ACD, then we would have BCD. So if we have an isosceles triangle, and we have at the top, the vertex angle has been cut in half, 2 equal parts, then we know that line CD drops perpendicular to the base AB. This right here, I'm going to make it solid so it stands out. This is dropping perpendicular to the base. Do you remember perpendicular means when it's coming at it at a 90-degree angle? And remember the symbol for perpendicular was an upside down T, capital T, because those come together at a 90-degree angle, right? Here's another beautiful thing that happens. When that drops perpendicular, it's cutting the bottom in half. So AD is congruent to BD. So a lot happens there. If you have an isosceles triangle, and at the top, that top angle's been cut in half, then it's going to drop perpendicular, and then the bottom would be cut in half. So basically, the picture, the triangle on the left matches the triangle on the right. You have 2 identical copies within that isosceles triangle. Okay. If I had to say the toughest one out of all of them, it'd be that one, just because there's so much info. But everything works out nice. Everything got cut in half. The angle at the top got cut in half. The bottom got cut in half. The 2 legs are equal. Looking at the bottom, let's look at this. Corollary to the isosceles triangle theorem. This is saying, what if it's not isosceles? What if it's actually equilateral? So basically, this is saying if all 3 sides are equal, so let's see, xy, so yz to zx. If all 3 sides are equal, then what do we know about the angles? Anybody? If all 3 sides are equal, then all 3 angles are equal. And then over here, they have switched it. If all 3 angles are equal, then all 3 sides are equal. So if the 3 angles are equal, then the 3 sides are equal. All right. So that's the front. The back is 10 practice problems. I need those practice problems to last through tomorrow's class, okay? So I want to flip over and I want to work on the back. And then I'm going to call people to my desk to talk to them about stuff that they're missing. Those 10 practice problems have to be completed by the end of class tomorrow. It's a grade, okay? Let me flip over to the back and look and see if I see any that are going to be like ridiculous. Number 10, if I had to guess, is probably the most challenging. Let's add one more thing to the front that you're going to want. Down here at the bottom, let me see who remembers this. If I know I have an equilateral triangle and there's not a single number written anywhere in the picture, what number do I actually know because it's equilateral, which means it's equiangular? I do know that the angles add up to 180. Yes. How many angles do I have? 3. I know what about the angles? What does the mark mean? They're all the same. So what would each angle have to be? 60. Do y'all remember this? It's been a few weeks. But we said anytime you have an equilateral triangle, meaning you also have an equiangular triangle, you actually already know all 3 angles are each 60. I cannot possibly write, I could maybe write it here. This is 60, this is 60, and this would be 60. So you know that every time it's in an equilateral triangle. That's going to be helpful when you get to the back, okay? You probably will need a calculator on this part, but I don't mind if, since it's just simple calculations, and I'm going to let you listen to music, I don't mind if you use your phone. I don't want to look out and see you actually snapping people or any of that stuff.